Let us consider the differential equation ay prime plus by is equal to 0, where a and b are both constants and a is non-zero. Now, this is both linear and separable. However, if we examine y prime, so solve for y prime, we'll get the form of k times y, where k is obviously some constant. There's only one function whose derivative is a constant multiple of itself, and that is the function e to the mx. It's the exponential function. Seeing this observation, let's plug y and y prime back into our differential equation. So we would have a times m e to the mx plus b times e to the mx is equal to 0. If we factor out an e to the mx, we get am plus b, and then all that has to be 0. However, e to the mx is non-zero for any value of x, or m for that matter. So this would mean that am plus b has to be 0. Now, for this single value of m that satisfies this equation, which happens to be, by the way, negative b over a, then the function y equals mx is a solution to this differential equation. We will make use of this observation and study higher order linear differential equations with constant coefficients. We will start by examining a second order linear differential equation with constant coefficients. What we do here can be extended into the more general higher order case. So what we're going to do is we're going to try the solution. So we guess the solution has the form y equals e to the mx. This would mean that y prime is me to the mx, which implies that y double prime is m squared e to the mx. Plug these values into the original differential equation. We get a times m squared e to the mx plus b times me to the mx plus c times e to the mx equals 0. If we factor out that e to the mx, we have am squared plus bm plus c is equal to 0, which means that am squared plus bm plus c must be equal to 0. This is a quadratic equation in M. So we'll wind up using the quadratic formula. Now, This equation is called the auxiliary equation for the differential equation. So now we use the quadratic formula and find that m1 is negative b plus the square root of b squared minus 4ac all over 2a, and m2 is negative b minus the square root of b squared minus 4ac all over 2a. You should recall that we have three possibilities. The first possibility is b minus 4ac could be greater than 0. If this is the case, we get distinct real roots. So both m1 and m2 are real numbers, and they're distinct from each other. We could also get b minus 4ac is 0, in which case it's a repeated real root. So we actually only have a single answer. m1 and m2 are the same, and it's a real number. Or b minus 4ac could be less than 0, in which case we get complex conjugate roots. So m1 and m2 are complex numbers, and they're complex conjugates of each other. We will now examine each of the three cases separately. We first consider the case where b minus 4ac is greater than 0, so the distinct real roots case. Well, in this case, we have two solutions. y1 is e to the m sub 1x, and y2 is e to the m sub 2x. We now show that these are linearly independent. So the Wronskian of y1 and y2 So we'll wind up with m2 e to the m1x times e to the m2x minus m1 e to the m1x times e to the m2x. We can factor out the e to the m1x times e to the m2x. This gives e to the m1 plus m2x times m2 minus m1. Now, e will never be 0, and we know that m2 minus m1 can't be 0 because m2 and m1 are distinct. So this will never be 0 for any value of x. And again, this is because m1 does not equal m2. So these are linearly independent, which means they form a fundamental solution set. And so our general solution will be y of x equals c1 e to the m1x plus c2 e to the m2x. So let's solve the differential equation 2y double prime minus 5y prime minus 3y equals 0. So the first thing we need to do is we need to come up with our auxiliary equation, which is 2m squared minus 5m minus 3 is equal to 0. We have to solve this. So if we factor this, we wind up with 2m plus 1 times m minus 3 is equal to 0, which gives m is negative a half or 3. So we have two distinct real values. So y1 would be e to the negative half x. y2 is e to the 3x. And so our general solution, c1 e to the negative x over 2 plus c2 e to the 3x. We now consider the case where b squared minus 4ac is equal to 0. In this case, we have only a single solution. Y is e to the mx. We're going to note that m in this case is negative b over 2a. Now we need to find a second solution. So we're going to use reduction of order that we studied at the end of the last lesson. So we find that y2 is equal to e to the mx times the integral of e to the negative integral b over a dx all over e to the 2mx. Simplifying, we'll get e to the mx times the integral of e to the negative b over ax all over e to the 2mx. Now we make note of the fact that m is negative b over 2a. So this here, this negative b over a, is twice m. So this becomes e to the mx times the integral of e to the 2mx over e to the 2mx. This is, of course, just 1, and so we wind up with x e to the mx as our second solution. This will give y1 is e to the mx, y2 is x e to the mx. Let's now verify that these are linearly independent. So the Wronskian of y1 and y2. So we'll get e to the mx times mx e to the mx plus e to the mx minus x e to the mx times m e to the mx. We get m x e to the 2mx plus e to the 2mx minus mx e to the 2mx, which is just e to the 2mx, which is not 0 for all values of x. So these are linearly independent, and so they form a fundamental solution set. So our general solution will have the form c1 e to the mx plus c2x e to the mx. So let's go ahead and look at the differential equation. Y double prime minus 10y prime plus 25y is equal to 0. So the auxiliary equation, m squared minus 10m plus 25 is equal to 0. This factors to m minus 5 squared equal to 0, which means we have a single solution, m equals 5. So y1 would be e to the 5x, y2 is x e to the 5x, and so our general solution is y of x equals c1 e to the 5x plus c2x e to the 5x. We finally consider the case where b squared minus 4ac is less than 0. In this case, our two solutions would be able to form m1 is alpha plus beta I, and m2 is alpha minus beta I, where alpha and beta are some real numbers. In this case, our solutions are able to form y1 e to the alpha plus beta I x, y2 would be e to the alpha minus beta I times x. This has the same effect as the distinct real roots. So our general solution would be able to form y of x equals c1 e to the alpha plus beta ix plus c2 e to the alpha minus beta I times x. However, we would prefer that our function be a real function. This is a complex function. So we're now going to make use of Euler's formula, which states that for any real number theta, e to the I theta is equal to cosine of theta plus I times sine of theta. Using Euler's formula, we can write e to the beta ix as cosine beta x plus I sine of beta x, and e to the negative beta ix as cosine of beta x minus I sine of beta x. Here we used a combination of Euler's formula along with the even and odd properties of cosine and sine. So, if we look at this, if we choose C1 and C2 both to equal 1, then we get y of x is equal e to the alpha plus beta I x plus e to the alpha minus beta I x, which is e to the alpha x times e to the beta ix plus e to the negative beta ix, which is e to the alpha x times cosine of beta x plus I sine of beta x plus cosine of beta x minus I sine of beta x. Which gives us 2e to the alpha x cosine beta x. Now, if we choose C1 to be 1 and C2 to be negative 1, then we get y of x is e to the alpha plus beta ix minus e to the alpha minus beta ix. We can factor out that e to the alpha x, and we're left with e to the beta ix minus e to the minus beta ix. This gives e to the alpha x times the quantity cosine beta x plus I sine beta x minus cosine beta x minus I sine beta x, which will give 2I e to the alpha x sine of beta x. Now, 2 is a constant, and 2I is also a constant. So we can conclude that y1, which is e to the alpha x cosine of beta x, and y2 is e to the alpha x sine beta x, are both solutions to the differential equation. And notice that these are now real functions. It is left as an exercise to show that these form a fundamental solution set. So we can therefore conclude that our general solution, y of x, is c1 e to the alpha x cosine of beta x plus c2 e to the alpha x sine of beta x, or e to the alpha x times c1 cosine of beta x plus c2 sine beta x. So let's go ahead and solve the differential equation. 4y double prime plus 4y prime plus 17y equals 0. Using the initial conditions, y of 0 equals -1, and y prime of 0 equals 2. So we first need our auxiliary equation, 4m squared plus 4m plus 17 equals 0. This cannot be factored, so m is -4 plus or minus the square root of 16 minus 16 times 17 all over 8, which equals -4 plus or minus 4 square root of -16 all over 8, which is -1 plus or minus 4i all over 2. So m1 is -1/2 plus 2i. m2 is -1/2 minus 2i. And so the general solution is e to the negative x over 2 times c1 cosine of 2x plus c2 sine of 2x. Using the condition y of 0 is -1, e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0, so we get c1 has to be -1. Using the condition y prime of 0 is equal to 2. Again, this is 1, or I'm sorry, we need to first find y prime. So it'd be e to the negative x over 2 times -2 c1 sine of 2x plus 2 c2 cosine of 2x minus 1/2 e to the negative x over 2 times c1 cosine of 2x plus c2 sine of 2x. So this is 1. This is 1, it's e to the 0. This goes to 0. So here we're left with 2c2. This is 1, 0, and 1. So we have -1/2 or -1/2 c1, but c1 was -1, so this becomes +1/2. This has to equal 2. This means, of course, that 2c2 is equal to 3/2, so c2 has to be 3/4. Therefore, our solution, y of x, is e to the negative x over 2 times negative cosine 2x plus 3/4 sine 2x. We will now generalize our previous discussion for the nth order linear homogeneous, so an nth derivative of y plus an minus 1 n minus 1 derivative of y plus so on and so forth plus a1 y plus a0 y equals 0. The auxiliary equation would be an m to the n plus an minus 1 m to the n minus 1 plus yada 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 plus a1m plus a naught is equal to 0. So for each distinct m, we get a term y sub I equals e to the m sub I x. If m sub I has a multiplicity of k, then it would contribute e to the m sub I k, x e to the m sub I k, I'm sorry, m sub I x's. X squared e to the m sub I x, yada yada yada, up until x to the k minus 1 e m sub I x. If m sub I equals alpha plus beta I is a root that has multiplicity of k, then so is m equals alpha minus beta sub I. And so we would get the terms e to the alpha x cosine of beta x, x e to the alpha x cosine beta x, x squared e to the alpha x cosine beta x, so on and so forth up until x to the k minus 1 e to the alpha x cosine beta x, and e to the alpha x sine beta x, x e to the alpha x sine beta x, x squared e to the alpha x sine beta x, so on and so forth up until x to the k minus 1 e to the alpha x sine beta x. So let's go ahead and solve the differential equation. 3y triple prime plus 5y double prime plus 10y prime minus 4y is equal to 0. Auxiliary equation, 3m cubed plus 5m squared plus 10m minus 4 is equal to 0. This can be solved to find that m1 is a third, m2 is negative 1 plus I root 3, m3 is negative 1 minus I root 3. So our general solution is c1 e to the x over 3 plus e to the negative x times c2 cosine of root 3x plus c3 sine of root 3x. And of course, this can all be expanded to fourth order, fifth order, so on and so forth. So that concludes this lesson. I hope you've learned something, and we'll see you in the next one.